Good morning, class. How you doing? Hope you had a good Halloween. All right, gang. So, happy Monday. Uh, Dia de los Muertos. So, your next exam. Let me take a look here. Just wrote this down. Your next exam is scheduled for a week from today. All right, that's on November 9th. And so we moved the last exam one day in the future because we were about one day behind. So I'm going to do the same for this exam. So this exam, exam 3, will be a week from Wednesday this week. All right, and same format as before. So that's November 11th, a week from this Wednesday. And the same format as before, quantitative problems, multiple choice problems. The content on this exam is exclusively momentum, right? Momentum, conservation of momentum, well, impulse as well, because impulse is part of the theory of momentum and it being conserved, all right? So that's what's coming up, all right, a week from this Wednesday. The homework problem set for momentum, which was scheduled due tonight at 11:59. I took a look to see how you were doing and decided to give you a few extra days. So that homework assignment is now due Wednesday at 11:59 p.m. Okay. When we are done with momentum, we'll turn our attention to capping off the semester by talking about rotational mechanics, applying a lot of what we already learned about kinematics, conservation of energy, and conservation of momentum to the situation where things are rotating instead of moving linearly, okay? All right, so what I want to do today is I'm going to keep an eye on the chat and see if you have any questions, but I want to work through one of the problems that was assigned, the very last problem, and the reason I want to do this is there's a part of that problem which is a mistake. It's written out incorrectly. It's not a huge deal, but there's something about it that's not stated correctly. All right, and so we'll take a look at it and work through that problem. And then if we have time, we will do some conceptual question work. All right. All right, gang, let's do this. All right, switching over to my whiteboard. All right, so let's take a look at the problem first, shall we? Bring it up here. Okay, so it's from what I can gather, there is some problem with this problem here, which has a tutorial that helps you work through, and so this is, I guess we can call it a modified ballistic pendulum experiment. Instead of the bullet getting embedded in the object, it passes right through. But the collision imparts some momentum to this object that's hanging down here. A piece of paper, is that what it's called here? So we worked through this on Friday, and I'll keep an eye on how you're doing on this problem and then reassess. So I posted a tutorial on this problem that should get you through. So this is the one I want to talk about right here. Two identical billiard balls collide. The first one is initially traveling at 2.4 meters per second in the x direction and 0.6 meters per second in the negative y direction. And the second one is traveling at negative 1.8 meters per second in the negative x direction and 2.7 meters per second in the positive y direction. And then they collide. They're billiard balls. And so the assumption here is they're going to collide elastically. All right. And it tells you where the balls are when they collide. So it says ball 1 is at the origin and ball 2 is at a point 0, 2r. So that would be on the y-axis, and r is the radius of the balls, so that would make sense. They have to be separated, their centers have to be separated by a distance equal to 2r if the radius is r. But what doesn't make sense is these things can't collide based on how they're moving with ball 2 above, which 0, 2r is a coordinate above the origin. They can't collide in that way. So what this really should say is 0 minus 2r. What's the final velocity of each ball expressed in vector form? All right, so that's the problem. Let's take a look at how you would set this up and solve this problem. All right. Alrighty. It's cold out there today. Alright, so this is an elastic collision between billiard balls. Alright, so it occurred to me that maybe your numbers will be different, but the signs will be the same because they're not in red for the initial velocities of these billiard balls. But the first one is sort of on a course that is positive 2.4 meters per second, I hat, negative 0.6 meters per second, J hat. So its course would be something like that. So we have V1 initial equals 2.4 I hat minus 0.6 J hat. Meters per second. And then ball 2 is down here. And it's on a course, something like that. And its velocity is, for my problem, minus 1.8 I hat plus 2.7 J hat meters per second. So it's traveling up and to the left. Ball 1's traveling down and to the right, and ball 2 is traveling up and to the left. All right, and then they collide, and so this is where the order is reversed. If they're on these trajectories, the way they'll collide is like this. And where it says ball 1 is on the origin and ball 2 is at a point equal to 0, 2r, 2 times the radius of the balls. And that would make sense. Okay, so do you guys know the significance of this? Do you know the significance of why you're told where their positions are when they collide? Does anybody know? Well, let's write out some conservation expressions and see if we can figure this out. And I'm looking at the chat window. Okay. So one thing we will know is change in momentum equals 0. Okay. So we have, and this is a two-dimensional problem, so we'll call to the right positive x and up positive y. Okay, so in the x dimension, what we have is the momentum of ball. And another thing is these are identical balls, so you have mass and mass, the same mass. They're billiard balls. They're identical billiard balls. It says it right in the problem. So the momentum before the collision of ball 1 is, in the x direction, is m times 2.4 meters per second. And the momentum of ball 2 in the x direction is m times minus 1.8 meters per second. So the total momentum in the x direction before the collision is this. And then after the collision, it would be m v1 final x plus m v2 final x. Okay, so all of these masses will cancel because they're all identical, and this will simplify to 2.4 minus 1.8 is 0.6. So the sum of the x components of the post-collision velocities have to add up to 0.6. All right, let's take a look at the y direction. Okay, so Holly's got put in the comment while we're looking here some knowledge about this collision that may be useful. So Holly says they bounce off each other in a specific way that their horizontal velocities stay the same, albeit in a opposite direction. Okay. So I think so part of that is true. The second part, I'm not sure about, but we'll come back to that thought. Okay. But definitely the way they collide is important here. It allows us to drastically simplify things. Okay. So in the y direction, let's keep working on here until we hit a roadblock, and then we can reconsider what the nature of the collision is. Okay, so in the y direction we have the first ball 1, has a pre-collision momentum of m times minus 0.6. Ball 2 has a pre-collision momentum in the y direction of m times 2.7. Okay, and that's going to equal the final velocity of ball 1 and ball 2, the final momentum of ball 1, which would be mv1 final y, and the final momentum of ball 2. And so just like in the other expression, all these m's will cancel, and we get this relationship that so 0.6 plus 2.7 is 2.1 equals v1 final y plus v2 final y. Okay. And okay, so we have 2 equations here and 4 unknowns. Okay, so that's not going to be enough for us to solve things, but we can also consider conservation of energy, which would give us another equation that we could write out. But still, it seems like, well, then we'd only have 3 equations and we'd still have 4 unknowns. So it looks like not enough information is given for us to proceed. So let's revisit the nature of the collision. Okay, and so what this is saying is that if the collision happens like this, where the balls are stacked vertically, that the force of the interaction is directed straight up and down. Okay, And if you multiply that force, let's think of it as an average, by the amount of time that interaction takes, what that gives us is a change in momentum. Okay? For each of these balls, that's impulse. Oops, forgotten an S. Impulse. And so impulse is a vector quantity. And right, so Holly's got right now, never mind, I said opposite direction when referring to the y direction. That's correct. Okay, so ultimately what we're going to find out here is, well, okay. Let's take a look here at this picture. All right, so this impulse is a vector quantity, and what this is telling us is that the nature of this collision, where they're stacked one on top of each other, means that that vector quantity impulse has no horizontal component. All right, there's no horizontal component to that impulse. There's only a vertical component. All right, there's no horizontal component to the impulse, only a vertical component. So what that means is, impulse is a change in momentum. So if there's only a vertical component, that means the horizontal component of each of these balls' momentum is not going to change. It's only going to change in a vertical direction. All right. So that actually, well, that gives us half our answer already. Let's go to Chrome. Okay. Well, since the impulse is vertically oriented, the momentum of ball 1 in the horizontal direction is going to be the same. Okay, and the horizontal component of ball 2's momentum is going to be the same. It's 1.8 meters, kilogram, meters. Well, the masses are the same, so this is just going to be, negative sign missing. Here we go. So what remains is to figure out the y component. So Holly has some intuition here about what's going to happen, and this wrong source. This is coming. Remember when we started momentum, we looked at collisions between objects that have equal mass, and that was a special case of a collision where two objects collided and they exchanged velocities along the direction of the collision. And so that's going to happen here because these two objects have each equal mass. So I already know the solution. The change in momentum is all oriented vertically, so that means there's no change to the horizontal momentum, and thus no change to the horizontal velocities. All the change is due to this vertical interaction. So they're going to switch. So I already know the answer here. So ball 1 is going to get ball 2's initial velocity in the y direction. And ball 2 is going to get ball 1's initial velocity in the y direction. And that's correct. So their horizontal velocities are unchanged and their vertical velocities are switched. Oh, whoops. Here we go. I forgot to change sources. So their horizontal velocities are unchanged and their vertical velocities are switched. The vertical components of their velocities are switched. So V1's y component is 2.7 after the collision, and ball 2's is negative 0.6 after the collision. Okay, so let's go back to here. And all right, so then we could write out that the change of momentum in the y direction for ball 1 is going to equal sorry. Oh. So the change in momentum of ball 1 in the vertical direction is its final momentum in the y direction minus its initial momentum in the y direction. And then to change the momentum of ball 2 in the y direction, it's going to be m v2 final y minus m v2 initial y. And the physics of this interaction is that these two impulses are going to be equal in magnitude but opposite in direction. They're equal in magnitude and opposite in direction. This is a statement of conservation. So we would have, and all the m's will eventually cancel. Well, we'll keep them for now. We'd have m1 mv1 equals m v2 initial minus m v2 final. And all the m's will cancel. So you have this relationship between the initial and final velocities. So now you have two equations with two unknowns, and because v1 initial and v2 initial are known, so you can solve for the two unknowns, and you will get this answer that we just found, that the two the y velocities switch direction. Actually, we didn't write out the second equation. Whoops, I just wrote out two versions of the same equation. The second equation will be the conservation of kinetic energy expression. There's no change in kinetic energy horizontally. There's no change in kinetic energy vertically. So if you write that expression out, then you'll have two equations with two unknowns, and then you can solve for the two unknowns. Okay. So I have a question for you. This is a conceptual question, all right? So I got 18 of you on here right now. So let's get active in the chat window here. All right. Here's the situation. All right. You are, well, here, got a door over here. There's a door over here. And I'm feeling lazy. So I'm sitting over here in my lab here at home, and I want to close that door. And I look around, and I got a bouncy ball, or a ball that bounces, and I got a ball that's made out of clay. All right. So it's really tired today, and I only have energy to throw one of these balls. Okay. So I have these two balls. One's a bouncy ball. I guess it could be a baseball. Baseball bounce. And the other one is a wad of clay. All right, and I'm gonna throw one of those balls at the door to get it to shut. Okay, and they both have the same mass, and I can throw both of them equally hard, equally on target, but I can only throw one of them. And I don't want to fail. I want that door to close without me having to get up. So what choice do I make? Which of those balls will I throw to maximize my chances of shutting that door without getting up? That's the question. There's the door. Here I am. Throw ball at that door, one is bouncy and the other is a wad of clay that doesn't bounce very much. So we got one answer in here. Tyler says clay for sure. Clay for sure. All right. So talk about it. Holly says clay. Chris says clay. So can you justify that? Can you you got to break this down and think of what's the difference? Is there a difference? Clay. How's clay going to behave when it collides with the door compared to like a baseball? Thomas says the baseball. So now we got 4 for the clay and 1 for the baseball. But still, you guys are just saying one or the other without any justification. Can you justify? Chris says the clay is less elastic. That's true. That's true. The clay, so there's collisions here. Collisions between ball, object, and door, object 2. And the difference is if I choose the clay wad and throw it at the door and it collides with the door, it's going to collide a lot less elastically. It might even stick. It might even stick to the door. Okay? But the baseball will bounce, definitely, be more elastic. When it hits, it squishes against the door and should transfer more of its momentum, right? That's interesting. Clay is inelastic and transfers the kinetic energy differently. That's true. So you can start thinking about kinetic energy because obviously whichever of these collisions transfers momentum and energy more effectively to the door is going to be more likely to shut the door. So that's definitely true. All right. So let's think about the collision. All right, because I think I got to direct you here. During the collision, the way we would think about the collision is with the physics of impulse. All right, impulse is a force multiplied by a time, and it's also a change in momentum. Okay, so one way to answer this question is which of these scenarios delivers the most impulse to the door? All right, the clay is inelastic and transfers the kinetic energy differently. The clay ball is likely to hit the door and stick while the baseball would bounce, thus causing the door to shut with more force due to the fact that there would be less outside force acting on it. Okay. I mean, you guys are thinking about this. You're starting to think about this the right way. You're getting closer. You're not quite there yet, though. Not quite there yet. All right, let me direct your attention to this concept of impulse a little bit more. All right, and all right, so here is an example of this concept of impulse in action. And you have a force during collision, and so the principle of momentum conservation comes out of the fact that and this is a consequence of Newton's third law, that when these billiard balls collide, the impulse experienced by ball 1 is equal in magnitude but opposite in direction to the impulse experienced by ball 2. Okay. So, which ball, so then it becomes, when it comes to the balls colliding with the door, the balls are going to experience an impulse, the door is going to experience an impulse. What you want is the door to have a large impulse, as large as possible. So then you ask yourself, well, which scenario has more impulse? A clay ball colliding or a baseball colliding and bouncing? All right, Thomas says, would it have to do with the chance of the clay deforming on impact and taking more force from the throw? thus causing less of the impulse on the door. So whatever, so that definitely matters. But our working assumption here is that it doesn't matter how sticky the clay is going to be less elastic than the baseball. All right, so in the two extremes, you have on one extreme the clay is completely inelastic, it collides and sticks. And on the other extreme, the baseball is perfectly elastic, so it bounces with 100% elasticity. Okay, so neither of those extremes are true, so Colton has hit on something here. The larger impulse will be with the baseball. Why? Can you explain that a little bit better? Why? You might think, well, change of momentum, that's impulse, and the clay wad goes boom and stops. You know, if it sticks to the door, it basically stops. That's a pretty large change in momentum from something to nothing. But Colton says the baseball has a larger change in momentum, and I agree. But how exactly does that work? How exactly does that work? So the baseball would bounce off and change directions, but keep much of its kinetic energy, thanks to elasticity. All right, so the key word there in William's comment is, in Colton's here, the ball will bounce rather than stopping, which causes the door to react the same in the opposite direction. So the key words in these comments here is change in direction. All right, so let's go back to my whiteboard here. So if you have one object that's coming in with some velocity, before, and then after it collides, it stops, just collides with the door and stops. Okay, versus an object that changes direction. Which of these has a bigger delta P? This one. This has a larger change in momentum, because momentum is a vector. So direction matters. Put numbers here. If this was traveling at 1 meter per second and was 1 kilogram, its change in momentum would be 1 kilogram meter per second. But if it bounces perfectly elastically and goes from +1 to -1 meters per second, then the change in momentum is, sorry, let me back up. In the first case, the change in momentum is -1 kilogram meter per second. In the second situation, the change in momentum is -2 kilogram meters per second because of the change in direction. So, in this lazy scenario, which turned out to not be so lazy because you expended a lot of energy thinking about it, you only get to throw one ball. You should throw the ball that bounces the best, because that bounce represents a large change in momentum, and that bounce representing a large change in momentum means it imparts a large change in momentum on the object it collides with. Okay, so let's talk about now, let me see, good. All right, let's talk about a different situation now. All right, so the situation is car safety, and the safety devices in automobiles include Seat belts, physical restraints that keep you from falling out and bashing your head against stuff in the car. Um, but there's many more safety features in automobiles these days. A seatbelt will keep you from falling out, but seatbelts don't do as much to cushion the blow of of a collision compared to airbags and features in the actual structural design of the frame of the automobile called crumple zones. So crumple zones are these regions. I saw a video once. I won't show it on this live stream because it's on YouTube itself. But there's a video of I think it was a Volvo, and the idea is that parts of the frame of the vehicle are made of softer metal or less rigid structures compared to other parts. They're made to bend. So in the event of a collision, there's these regions of the frame that are designed to crumple first. And the reason you want to do that is so that you can control what parts are being deformed and where the components in the engine are going when you have a collision. It's like, the language in this video was that all components of the engine in the engine compartment have a predetermined position pre and post collision. All right, but the common feature in all of these things, crumple zones and airbags, is and we can think about it now. We can think about collisions using two different complementary physics. We can think about what's happening in terms of work. Work is the dissipation of energy. This is work done by non-conservative forces. Things deforming, lots of friction, internal friction in these structures. Work being done by non-conservative forces dissipate the energy during a collision as heat and deformation and sound and all that stuff. And we can also think about collisions in terms of impulse, this change in momentum, which is a force multiplied by time. So if you're thinking about collisions in terms of work, there's impact forces multiplied by distances, F times delta x's. And if you're thinking about collisions in terms of impulse, you have forces multiplied by delta t's. Okay, so put your mind there, and in the chat window here, let's see if you can explain how, you can use either of these two dimensions of physics or both. Can you explain how a crumple zone or an airbag saves a person's life in terms of the physics involved during the collision? All right. The physics of airbags. So Tyler's got a response here. The crumple zone is the recipient of the impulse rather than you. Well, you are. All right. Let me frame you here a little bit more. What saves your life is how your impulse occurs, or how you're part of this moving vehicle, and what saves your life is how your energy is dissipated or how your momentum is changed. Okay, so you got to think about the perspective of the person in the car, and how do these safety features affect that person's experienced during this collision. The airbag lessens the impulse of the car crash. Nope, that's not true. It doesn't lessen the impulse. Because let's think about it this way. If the car is traveling at 10 meters per second and comes to rest, it doesn't matter if you know what the car is made out of or what safety features it has. If it's traveling at 10 meters per second and comes to rest, that's an impulse. That's a change in momentum, a change in kinetic energy. Like how the airbag against you acts like clay against a door, if that makes sense. Yes, kind of, Holly. But not quite, because you can have you know, if you think about, you know, the steering wheel in your car is padded with a very, you know, it's like metal underneath there, and it's got this thin layer of foam padding on it. These the steering wheels in my vehicles are, and that padding is like a very, very teeny tiny little airbag, but why isn't that very sufficient? Because the airbag absorbs the impulse of the person. It does. The airbag absorbs the energy of the person and generates the impulse that the person experiences. But the dashboard or the steering wheel would do the same thing, and it could do the same magnitude of impulse. All right, because if you're traveling and you come to rest, it doesn't matter how you come to rest, the impulse magnitude is going to be the same. So it's not simply about the magnitude of the impulse or the magnitude of the change in work of energy, the work done. So you don't. Let's write out these expressions, okay? So you gotta. Oops. All right. So impulse is a change in momentum, and we can write that as F. Let's just write it like this: F dt, delta t. Work in the work energy theorem is a change in kinetic energy. Work done by non-conservative forces equals F dot dx. Okay, I know these aren't the calculus versions of these expressions, but if you're thinking about impulse, you have this. If you're thinking about work being done that slows down your kinetic energy, you have this. So both of these expressions have forces in them. Okay, so is it the rate of change? So you're getting closer. Okay, Thomas says it's the rate of change. William says it's flexible, so it does it more slowly over a longer distance. Now you're hitting on it. Upon impact, there is a force upon each car, and the airbag must produce a force relative to the force of the impact to replicate that force to attempt to safely stop you. That's true. So Colton, there is going to be an equal and oppositely directed force. Okay. But William is hitting on it. William is hitting on it. He used the word slowly, which has to do with time. All right, that's delta t in these expressions, and distance, which is related to displacement, the delta x in these equations. All right. So if you look at these expressions, the thing that saves your life is making F small, the force of impact. Okay? You want to minimize the force experienced by a person during a collision. You want to make it smaller. And the way you can do that is for a given change in momentum or a given change in kinetic energy. So what I'm saying is these two quantities held fixed. How can you reduce the amount of force someone feels? You can increase the amount of time or similarly, the amount of distance over which that force is exerted. All right, the airbag bends to the shape your face does. Right, so here's the thing. If you want to reduce the force of impact, what you want to do is increase the duration of the impact. And that can be in time or the distance over which the impact occurs. That's a displacement. And how do you do that? By using crumple zones in the car that squish, that increases the amount of time and the distance over which the impact occurs, or by using airbags, which slow you down more gradually. Okay? So the net effect is the same. If you slow down quickly or slow down more gradually, the total effect is the same. You go from moving to at rest. All right? But what matters is the force required to create that change can be dramatically lessened by increasing the amount of time or the distance over which that change occurs. All right, so you think about this, in collisions we're talking about fractions of a second. But if you take if an airbag takes the amount of time it takes for your body to come to rest from 1 millisecond to 10 milliseconds, 10 times as much time, that reduces the force that your body experiences by a factor of 10. All right, that could save your life. Okay, the force that you experience is what breaks bones and squishes internal organs and all that morbid stuff. All right, so on that note, let's call it a day. And I'll see you guys tomorrow for the lab this week is posted. It's another conservation of momentum or conservation of energy / impulse / momentum lab, dealing with a concept called coefficient of restitution. So we'll meet tomorrow afternoon and go over that lab briefly. And I'll show you how you can easily swipe in new videos without having to change your setup, and this lab has a lot of videos, and I'll make the analysis more quicker. All right, I will see you then. Have a great day.